is atomically ordered complex materials via control of entropic mixing. To begin, I'd like to thank the contributors on this project, which include my project director, Dr. Adam Hauser, and a graduate student that I've worked very closely with, Ridwan Nahar. I'd also like to thank the National Science Foundation for their funding of this project. So to begin, why should we care about atomic ordering? So in the 1980s, 99% atomic ordering was achieved for two-element materials. And what this led to was high-frequency transistors, which led to the cell phone revolution and high-efficiency solar panels. Now, we predict that accurate atomic ordering of three-element materials will have many more applications in information technology, solar cells, lighting, microwave communications, thermoelectrics, and power electronics because of its increased complexity. Now, what materials do we actually care about in this research? We focus on Heusler compounds, which are intermetallic crystalline alloys with face-centered cubic structures. What this means are these crystals with semi-metallic properties that form in a structure where the most basic unit cell is simply a cube with an atom at each vertex and an atom on the face of each cube. And if you look in the red square on this graphic, you can see that the difference between these two materials is a swapped x site and y site. And this represents the difference between a full and inverse Heusler, which is which are the two structures we are focusing on in this research. So the research questions we are looking to answer are, can we accurately predict the atomic ordering of these materials? Can we grow these materials? And do these materials have the predicted properties? And again, atomic ordering is simply this ability to predict and to predict the way in which this crystal will form, including the exact sites of these atoms. So this research process is broken into two main components: a theoretical computational process, as well as an experimentation process, which involves growth and characterization of these materials. So to begin, these calculations are performed using a density functional theory software package. And density functional theory is simply the theory from which our calculations are derived, or our formulas are derived. And these calculations are performed on the University of Alabama High Performance Computing Center. Then this data is graphed and analyzed in Origin Pro. Now, what calculations are run? First, a set of self-consistent energy calculations are run for a series of lattice parameters. And this raises two important questions. What is a lattice parameter, and what is a self-consistent energy calculation? So a lattice parameter is simply the side length of one of the unit cells I mentioned before. So in this graphic, the distance between two gray atoms. While the self-consistent energy field calculation is a little more complicated. It is an iterative method to solving the electronic Schrodinger equation, which essentially solves for the energy and the wave function of the electrons in this unit cell. And so to begin, we select an approximate electron density, then we calculate the effective potential, and then we use the Cohen-Sham equation to solve for these energies and wave functions, and then add these wave functions in quadrature to get a new approximate electron density, and run it through this until we reach a convergence threshold that we set at the beginning. From this, we get a series of energies along with volumes of unit cells. And these volumes of the unit cells are simply the cubed lattice parameter because it's the volume of a cube. And we get a graph like the one shown here where we have a series of volumes and a series of energies. Now we use the Birch-Murnaghan equation to fit this, of which a simplified version is shown on the board. And from this equation, from this fitting, we are able to derive the lowest energy, which is at this vertex of this graph, which is simply the most favored entropically to form at that energy. So using this equation, we get that energy, and we also get the volume at which this energy is achieved. And from that, by taking the cube root of that, we are able to calculate the optimal lattice parameter for this material. Next, we do a variable cell relax run, which simulates more real-world conditions and allows for the cell dimensions to change slightly to correct for any error in our initial calculation. Then we run one final SCF calculation to get a very accurate potential energy because we do it on a larger range of electron momenta. And this also returns the magnetic and charge properties of these materials. So this is an example of what data output looks like for two materials, titanium-2 iron aluminum and vanadium-2 iron aluminum. And we have results for both the L21, which is the full Heusler, and the XA, which is the inverse Heusler structure. And as you can see, we have the optimized lattice parameter, the relaxed lattice parameter, and the cohesive energy of these systems. Next, we compare the cohesive energy of both the full Heusler and the inverse Heusler structure to see which is more favorable to form entropically, because the one with the lower energy is more favorable to form. And as you can see, for titanium-2 iron aluminum, the full Heusler structure is more favorable to form because it has a lower cohesive energy, while for vanadium-2 iron aluminum, the inverse Heusler structure is more favorable to form. We also receive data on the total magnetic moment and the absolute magnetic moment in these materials. Next, we move on to the density of state calculations, which return the number of spin-up and spin-down electron states allowed at a certain energy level. And we focus around the Fermi energy level, which is the energy required to add one electron to the system, and that is represented by the 0 level on these graphs. And as you can see in the first graph on the left, that this material is not very spin polarized. In other words, there's a roughly an equal number of spin-up and spin-down electron states allowed at this energy level, which returns a spin polarization of 0.11%. While for the graph on the right, you can see it's very spin polarized. The spin-down electron states are heavily favored here. So spin-down electrons will be heavily favored to enter the system. So this gives us an idea of some predictive qualities of what the conductive properties of this material will look like. Then we can define these properties more using the band structure calculation. And the band structure calculation calculates the the energies allowed for these electrons, basically, and it returns a valence band, which is the band of which is the energy of the occupied electron states, and then the conductive band, which is the unoccupied electron states, or the states in which electrons can be conducted through the material. And if there is a large band gap, then these electrons require a lot of energy to move from this valence band to this conduction band and be conducted through the material. While there's no band gap, these electrons can be freely conducted. And so, as you can see on the graph on the left, there is a band gap in this material, while on the graph on the right, there is no band gap. And what we do with these results is we can compare these results for, say, a single material and predict whether it's very conductive of, say, spin-up electrons but not spin-down electrons, and see if it has semiconductor properties. And we were able to derive all this from these results. Now we have predicted the atomic ordering of these materials, and we have predicted their properties. Now we have to grow these materials to see if they have the predicted properties. And we grow these materials in thin films using an off-axis magnetron sputtering system shown here. And what this does essentially is the atoms are ejected from a source and deposited onto a substrate to form this crystal. And this is done in a very specific environment that we create to make these crystals entropically favorable to form, and including controlling the temperature and controlling the magnetic properties of this environment. Then we use X-ray diffraction to characterize the atomic ordering of these materials to see if it formed in the crystalline lattice that we predicted it would form in, to validate our predictions. Then we use a physical property measurement tool to measure its conductive properties and its magnetic properties to see if our other predictions hold up too. Now we compare. Does what we predicted match up with what was grown? In other words, can we predict desired properties for the materials and then grow the materials that we want? Overall, this group is searching for trends in the properties of complex Heusler materials. And this graph represents the X site atoms we're looking at, the Y site atoms, and the Z site atoms we're looking at, creating this lattice of materials that we care about. And this group has calculated predictions for nearly 200 elements. And I have completed roughly 40 alloy calculations, and I'm currently working on the nickel 2 Y site, Z site series. Any questions?
How difficult is it to grow these materials in these precise crystalline structures?
So like I said, when we do the sputtering of these materials, we have to create an environment in which it's favorable for these crystals to form, and rather than they're just constituent elements or some amorphous glass structure, because we do have to control several environmental factors in order for these crystals to form, including the substrate that we choose based on the lattice parameter so that they form in the predicted lattice parameter and the predicted structure.
So in studying these three-element compounds, what kind of trends are you looking for?
So we're looking for trends that we can find either within elements, certain X site series, certain Y site series, certain Z site series, or in terms of their magnetic properties, in terms of their likeliness to form. But as of right now, we have a lot of data and there are many variables. So we are looking into using machine learning algorithms to eventually search for these trends because it's too difficult to do by hand.
What factors led to the selection of the elements you are investigating?
So previous research into what Heusler compounds exist led to the selection, as well as the materials that we care about are mostly materials that we can grow financially, because there's a certain investment for using heavier materials such as diprosium, which is on this graphic, though we are no longer looking into that because it's quite an investment into getting diprosium. So we look into elements that are cheap to make, cheap to buy, so we can feasibly grow them.
So you'd mentioned that the structure with the lowest energy would be the most favorable to find. And I think it was slide 12, the table between the two examples. Those energy values were pretty similar to those cohesive energy values. Like the magnitude isn't that large. What impact does that have on like the favorability of the inverse versus the regular?
So these differences are expected to be small because it's not that it's not that significant of a difference to swap an X site and a Y site. Though these materials, we do create an environment where it's favorable to form. So they vary slightly, but it's still significant in when we grow them that we do still predict that the one with the lower one will form. So these small values are expected. These small differences are expected.